Cool. So earlier this year, I was exploring circle starks, right, and basically trying to understand how the hell this like very weird new primitive based on spooky stuff that's apparently called Riemann rock spaces is supposed to work. And so I figured that as part of that, I would do a fun experiment and basically try like actually building the whole thing, right? So first, started off the usual way I do things, which is just like write it out in Python. The point is not to be performant. The point is to just understand how everything works from front to end, make sure that you have a prover and a verifier that actually works at all. But then at some point I decided I would try to like take this experiment a step further, right? And what I basically ended up doing is I ended up using first NumPy and then QPy, which is a CUDA GPU wrapper that follows the same interface as NumPy, to write a prover in Python where the underlying logic is vectorized, and so you're basically using Python to operate over long, big lists of numbers at the same time. And the actual like one-by-one work of doing all of the arithmetic is done on a GPU, right? So this is basically how we do AI, right? There's huge amounts of AI code that is written in Python, and it's basically the underlying logic is done with some kind of CUDA wrapper, like usually Torch, sometimes something else. And like it still manages to be extremely fast, basically because the Python is only doing this like relatively small amount of glue logic, right? So I figured, okay, fine, let's like try to do this exact same thing, but for circle stark provers. So this is an implementation of a circle FFT. So the code is surprisingly simple. FFTs were extremely scary up until I implemented them to like about the 5th or 10th time, and then at some point they actually just like eventually magically stopped being scary. FFTs were one of those algorithms where, like, even after I implemented them and even after I wrote an entire post on them back in 2021, I still thought they were scary. I think the only thing that's, like, even scarier than them was elliptic curve pairings. Like, that stuff is, like, maximum voodoo, okay? So, like, I'm actually happy that this stuff is hopefully just going to outcompete elliptic curves out of existence. So FFT is implemented, and underlying logic all being done in through a CuPy Python wrapper around CUDA on a GPU. Then this is circle fry, and specifically the folding step. So the folding step is similar to an FFT, except instead of taking the two different pieces and proceeding to the next round with both of them, you basically randomly combine them, and you keep going further. Actually, wait, this is the implementation that's just in Python. There is another implementation that like just does it vectorized, which is not this one. So this is arithmetization of Poseidon, right? So I got excited about this because people were starting to talk about how you can prove Poseidon hashes extremely quickly, and for a long time people were thinking like, oh, maybe you can only prove like maybe 1,000, maybe 2,000 hashes per second, and this stuff is like impractical. But then suddenly Starkware came out with like their super impressive numbers, and they're like, oh my dog, you can prove 500,000 hashes a second. And then it's like, okay, well, if we have that, then like we can basically skip half the Ethereum roadmap and like go straight to Poseidon hashing everything. So the one like challenge there is that we have to actually be confident that Poseidon is secure, right? And so we're not confident about that yet, but hopefully we should. And Ethereum Foundation, I think, will soon like announce some kind of program about like trying to encourage more people to participate in checking that Poseidon is secure. But basically, yeah, Poseidon is this hash function. Like I've always found it beautiful, just in its sheer and like extreme simplicity, right? And like a basic implementation of Poseidon, you can literally fit in like 8 lines of Python, right? And so this is not an implementation of Poseidon. This is an arithmetization of Poseidon. So like implementing verification of it inside of a Stark. And one of the fascinating things about it is that it's actually surprisingly compact, right? Like you can do an arithmetization of Poseidon inside only about 200 cells, right? So inside of your entire trace, you need only 200 field elements for each individual Poseidon call. Basically, it's like even though Poseidon only has, does have 64 internal rounds, it turns out that for each internal round, you only need like a couple. I think actually for each of the for each of the inner rounds, except for the first 4 and the last 4, it turns out that you only need actually 1 extra trace value. And the reason is this very weird trick where you basically you use powers of the MDS matrix instead of using the MDS matrix directly, right? And so it basically actually just wrote that out. And the arithmetization itself is only something like 50 or 60 lines of Python, and you can find this in the GitHub Ethereum research repo and read it yourself. And it's actually surprisingly not scary and not hard at all, right? So results. So proved over 10,000 hashes a second. So note, I'm a noob dev. This was my first time ever writing a CUDA kernel. Starkware did 500,000 hashes a second, and so I am absolutely certain that there are 50x optimizations somewhere here that I am completely missing, right? And at the same time, you get code that is surprisingly easy to read and that is surprisingly accessible, right? So when I did this, right, so this is probably the first time anyone's written a prover in Python that can actually do serious work. It's and it was still surprisingly not that difficult to do. So at the beginning, basically all of the code was put in this one single file, and you just do everything directly on top of the QPy library, right? So then I decided, well, why not actually take the code that is specific to optimizing M31 related modular operations and just put it into a separate library, right? So we have Torch, which is a library that basically does, it's like CuPy, it's kind of a CUDA wrapper, but it also has a huge amount of extra optimizations that are specific to doing AI code. Let's do something similar to that, except instead of optimizing for AI code, let's optimize specifically for the needs of zero-knowledge provers, right? And so here, this whole file, basically you have an implementation of all of the different mod Mersenne 31 arithmetic, and then further down, I also have extension field multiplication, also have extension field modular inversion, regular modular inversion, all kinds of things. Again, definitely done totally not optimally at all, but even still, right? You basically can package this into this really nice and clean library, and what you get as a result is you get code like this, right? And basically, if you think about what this arithmetization is doing, inside of here, you just have expected equals prev plus RC times 5, and it looks like plus, it looks like times, and then in a circle Stark, sometimes you have to run the constraint checking function over the base field, sometimes you run it over the extension field, and then here you just have an abstraction where you just write the code once and it just automatically does both, whichever one you need depending on context. So basically, that's the idea, right? It's you write this code once, and then you can have this super beautiful, super clean code that just does everything that you need. So basic principle, right, is AI code is written in Python. So this is a screenshot that I've taken out of some code from a transformer implementation, and I'm sure the nerds here understand exactly what it does. I mean, it's a forward pass of a transformer, and basically, why Python? Because Python is the best language, right? Python is the apex of readability and good aesthetics. The problem is that historically Python is just crazy slow, but because we're dealing with vectorized computation where you can create Python objects that are individual objects that wrap potentially millions of numbers that you can just do, lists of billions of numbers that you can do computation around simultaneously. And so basically Python overhead actually ends up not mattering, right? And so I wrote a post about 2 months ago. It was called on this topic that I call glue and coprocessor architecture, right? Where the basic principle is that for any kind of what you might call hard computation or intensive computation, you can almost always, in practice, split it up into two parts, where one of those parts is like very general purpose computation, but fundamentally light computation, and then the other parts are heavy computation, but computation that is very, very structured, right? So like one example of structure is in AI, AI is basically just vector matrix multiplication, and like basically vector matrix multiplication is like one specific way of doing additions and multiplications on massive lists of numbers at the same time. And so basically, you just create specialized modules that are really thoughtfully designed around the specific task of adding and multiplying lists of numbers, and you like really optimize the heck out of those, put a lot of work into them, and then you have these nice clean abstractions, and then you can just work on them in some language that just optimizes for readability and just shows you the actual logic of the code that is being done, right? And in the case of ZK work, obviously, the more common structure is polynomials modulo like some prime number and in extension fields. And also, sometimes you actually get vector matrix stuff, like we have R1CS, but it does seem like the faster stuff these days is polynomial based, and then now we're also talking about polynomials over hypercubes now, and so you have like lots of these abstractions that just basically mean do operations over massive lists of numbers at the same time, and like you do that in the fast language, and then you do the high level logic in the slow language, right? So basically, the prompt here is let's code provers that are in Python as well, right? So this is just like a random part of the prover logic here, right? Basically, I mean the thing that's happening here is basically that in the constraints checking polynomial, you want to like prove that it has the starting value at the starting coordinate, the ending value at the ending coordinate, and so you just like divide it and like interpolate by the by the line that passes through those 2 points, and and you generate the quotient, right? And like you see it's like, hey, trace minus I over v. It just looks really nice and clean and beautiful, which is the way that code is supposed to look, right? So this is all again like basically just like an experiment by myself, and I think part of the goal is also to try to just make this whole space more accessible. So other existing work that I know about, so Icicle from Ingonyama, of course, great work here. I've looked at looked at the repo, and it seems like there's like no no Python support yet, but there is intent to do Python support, and so if this and like could just like merge and like we have a nice library that does what we need to do with Python, then I personally would be overjoyed. Also, QPy and PyTorch themselves obviously have massive optimizations in them, and I think some of those optimizations are things that are relevant to doing ZK as well, right? So like I'm sure they have stuff that's to do with like optimizing memory usage and like doing operations in place when some computation is not needed anymore, operations to do with like precompiling kernels and then like executing them all at once, and a whole bunch of crazy stuff. But then they do have other things that are just like inherently optimized for AI, right? It's like if you look at PyTorch, it has support for lots of different floating point types. It has support for like doubles and like float 16s and all kinds of stuff. But it like I think it does not even have like, at least when I used it, it did not have uint32, right? And like and of course for this like you need uint32, right? And so the direction in which you'd add certain features is going to be somewhat different if you want to go in the cryptography direction. And so I think if you have like some combination of these things, then you're able to make something that's much better than like that's just like a really nice library that you could use that just make it very easy for people to write these kinds of optimized provers for all kinds of algorithms. So conclusions, right? Basically, this is Accelerate ZK, and my plea for today is let's accelerate ZK developer time. So I view this as being like somewhere in between SIRCOM and like full-on like advanced people doing advanced stuff, right? Basically, yeah, SIRCOM is like make it very easy to write circuits, but at the same time it like hides huge amounts of logic in the background. The outputs, like not very inspectable. Like it makes the arithmetizations, and generally we're supposed to just trust them. Whereas here, this is like the idea is that we can create these like more middle-level toolkits and basically create things that still expose the fundamental mathematical components, and that basically are not like even make the not just like long-running existing algorithms more accessible, but also make more accessible frontier stuff where you have to like fiddle with the algorithms yourself, where you have to make like really crazy custom arithmetizations, where you have to like work over different fields, you have to work over different types of snarks. In Zorch, one other thing that I did not talk about is that I also wrote a Binius implementation a bit earlier in the year, and so I just like folded the binary field stuff from that into that. And so basically, like, let's like actually make these more crazy and more frontier aspects of ZK accessible, and like basically learn from how the AI space has made very performance-intensive code very hacker-friendly. And so the call to action here that I have is basically like, I'm a blogger, I'm a noob dev, I wrote stuff, and encourage people to like basically just take it and like build on it and like combine different components together, and let's like create something that makes it actually practical for people in like Python or any language to just like go and write provers that can do things like 500,000 Poseidon hashes per second with any of these new algorithms that come up. So thank you.
Vitalik is building ZK tool for us. Oh my God. Questions?
Hi,
Yeah.
nice talk, thanks. So I'm one of the designers of Poseidon. You talked about it a lot. There's Poseidon 2.
Yeah, actually this was Poseidon 2.
Yeah. So we could do a Poseidon 3, tweaking a little bit more, making it a bit faster. Of course, this might erode some of those 5 years of trust. So what's your take on that?
Interesting. So actually, I'm curious. Like, how much do you think you'd be able to optimize like the arithmetization further? Right? It's like 200 cells for Poseidon 2. Like, how many for Poseidon 3 if you try hard?
Yeah, I mean, without changing the design too much, it's not going to be that big. I mean, there's totally different hash designs where we can do much faster, but that's then starting from scratch, basically. So maybe 20–30% at most.
Right, 20–30%. I mean, I think it would help. I think it's. I mean, the question is then, like basically how much of the like security analysis does it inherit? I think, I mean, I imagine, if you're a co-author of Poseidon, you're in touch with Dmitry, and like you probably know that Dmitry has been working with the EF, and like we've been starting to do this like big academic analysis effort. So I think it's definitely encourage you to be part of that. And I think ideally we would like try to get as much security assurance as possible, not just about like Poseidon 2 itself, but also about the general category, and try to understand like what are the things that are safe to tweak. So I mean, I personally would obviously love to see Poseidon 2 become even faster. I mean, the counter argument, of course, is that like we can these days prove like 2 million hashes on a GPU, and it's like basically enough to do almost everything. And so like the thing you want to optimize is for like basically like harder security assurance, but like those are trade-offs that can go in either direction as well. So I'd support both.
Okay. Makes sense. Thanks.
Anyone else? I'm curious, what are the long-term plans for Zorch?
I mean, realistically, like, I'm too busy to have long-term plans personally, but, like, my wish is basically for, like, Icicle people and other smart people to, like, basically take Zorch and, like, build something that has, the Zorch API plus more that, like, actually, incorporates all of the crazy, optimizations that can, like, actually get you to 500,000 hashes a second.
We're happy to do it.
Amazing. I look forward to it.
Another one?
Yeah. You showed 10,000 Poseidon 2 hashes per second. Was that on the CPU or in Zorch?
This was on a GPU. So this was on my laptop, which has a 4070.
Okay, thanks.
Hi, yeah, I have a question. So regarding Zorch and how kind of the programming model works. So in PyTorch, there's kind of two modes. There's like eager execution and there's kind of a compiled version, right? So currently, does Zorch only support eager? So
currently, it only supports eager, and I fully understand the theoretical arguments for why like the lazy and precompiled approach is better. And I think someone who knows already knows the best way to do that stuff should like ideally just go and do it.
Fair enough. Okay. Cool. Thanks.
Great. I have last one.
Yeah.
So people are claiming that ZK will be the end game for Ethereum. So I'm curious how to define this end game.
So I don't think ZK itself is the end game. So in the last one of my posts where I talked about the future of the Ethereum roadmap, like the 6th one, I talked about the 3 Egyptian god protocols, right? So ZK snarks are 1, FHE is the 2nd, and obfuscation is the 3rd. And then there's like the even crazier one, which is one-shot signatures, which requires like users to have quantum computers. And so I think out of those, like ZK is crazy powerful. FHE is like important, but it turns out that it has relatively less intersection with Ethereum, basically because everything in FHE, it involves this trust model where you need like someone or some NPC or something to have the backdoor key to actually do the decrypting at the end. Obfuscation removes the need to have that backdoor key. And so obfuscation is like potentially insanely powerful. Like it can do everything, right? And like in my post, I actually talked quite a bit about like some examples of applications like voting and like what power FHE can add, what power obfuscation can add. And I think that stuff is amazing and we should do it. But of course, obfuscation is like, my impression is that basically, it only started being like a thing very recently, because before that we did not have actual implementations, or before that we didn't even have actual protocols. Then in 2020, there was the first actual protocol, but then someone tried to figure out how to implement it, and they estimated that it would take 10 to the 27 years to run. Then a year later, someone did some optimizations, and they figured out that actually they would only need 1 year to run it. And so it's like, yay, we're almost done. It's like logarithmically halfway there, right? It's like 10 to the 27 years, then you go to 1 year, and then if you could do 10 to the minus 27 years, you've won. I mean, actually, if you do 2 to the minus 27 years, that's like gonna be only about 30 seconds, so then you've won already as well, right? Wait, did I do that math right? No, it'll be a quarter second, and then we've won as well, right? And so, in some sense, we're almost there, but like practically speaking, it feels like we're in that regime where it reminds me of like where ZK snarks were in maybe 2010, right? It's like on that curve toward like practical implementations that you can do. And so I expect, but that like this time there's a lot more eyes on the problem, and so I hope obfuscation will improve much faster, and that's going to enable a lot of really crazy stuff.
Thanks. Guys, you got more to learn and build. Okay.
Yeah,
thanks. Thanks,
Thank you.
Khop Bun Ka.
Khop Bun Ka.